Hello all, welcome to lesson 7. Today's topic is continuity of a function at a point. Lesson 7 and 8 are in the same packet, so you shouldn't be looking for lesson 8 separately. It's all together. The homework will be in the end, so be careful about that. Okay, let's get started with the warm-up. A graph is given to you and it's asking limit as x approaches 2 of f of x. From the left, let's trace it. What is it? It is approaching, the y value is 6, right? So that's what my limit is from the left. From the right, if I trace as x is approaching 2, my y value is what? 4. They're not approaching the same number, so the limit does not exist. So you should all be very good with this. We're already in lesson 7. If you still are having difficulties with limits, please go back to my previous videos and previous lessons. Redo those questions. Please email your teachers about any questions or concerns you have, because you really need to know this material. Okay, so now when it says f of 2, that means what's the value when x is 2? So what is the value? It is where the circle is filled. I'm going to erase this so that we can see it carefully. So f of 2 is, it would be this value, which is, happens to be 6. Okay, limit as x approaches 5 of f of x is what? Just check. As it's approaching 5 from the left, it's approaching 7, right? It's approaching 7, so it is 7. And f of 5 is 7. Okay. So we have another part to it. It says, is f of x continuous at x equals 2, y or y not? First, let's understand what continuous and not continuous means. Anytime we are given a graph and we want to determine whether it's continuous or not continuous, I would say just trace it. As I'm tracing it from left to right, I had to pause and I had to lift my pencil to keep tracing my graph, right? And then I trace the rest. So the minute you stop and pick up your pencil to trace the graph, it is not continuous. And if you can continuously, without lifting your pencil, trace the whole graph, it is continuous. And especially if you want to find out at that value. So I hope that will make you understand the next two parts of this question. So it says, is f of x continuous at x equals 2? So at x equals 2, I'm going to circle that, right? What happened here? When we were tracing it, I traced from the left and then I had to lift my pencil to trace it further down. So it's not continuous because I had to lift my pencil, but you cannot write that as your reasoning. No, because limit as x approaches 2 of f of x is not equal to f of 2, right? And if you look up here, they're not the same values, so it does not exist. Actually, when it is like that, it's called a jump. There's a jump happening here, and we'll learn more about it later in the video. Okay, next thing it's asking is f of x continuous at x equals 5? So let's go at x equals 5 and see what's happening here. At 5, if I was to trace my graph here, isn't it continuous? So yes, it is continuous. So let's write that down. Yes, because, and another way of checking it is here. The values are same. So that's your explanation. Limit as x approaches 5 of f of x equals f of 5. So that's it. So today our lesson is to learn about different kinds of continuity, and I just wanted to go over these few pictures. So we just talked about continuous, right? Most of the applications of calculus require that functions be continuous. A function is continuous if you can draw it in one motion without picking up your pencil. That's basically what I said. I want you to highlight that so that you can retain it and remember it. So if I was to trace, look, this graph, this is continuous because as I'm going around, I don't have to lift my pencil, whether going from left to right or right to left. I always like to trace them from left to right, and that's how you should do it. Okay, but the next one, if I look at this, should do it in here, look here. there's a hole. I had to pause and then lift my pencil and then trace the rest. So this is not continuous, right? So whenever you see a hole, a vertical asymptote or a jump, so I have a hole here, a hole, vertical asymptote, you see that, right? X equals C, and a jump, the graphs are not continuous. So let's talk about the definition of continuity at a point. This is the fancy definition. A function is continuous at a point x equals c if the following is true. So this is your fancy definition, right? What does it basically mean? Left limit, if your left limit is equal to the value and is equal to the right limit. So if the limit exists and it's equal to that value of that function at that point, then it is continuous. Or in other words, what can I say? If a function is continuous at a point, if and only if the function value and the limit value, and that's what I said, right, are the same. So there are four types of discontinuities and you've seen them. We've really not talked about much in the past. So let's talk about them. A removable or point. You'll hear me say removable for most time because it's very relatable and you'll see how. Discontinuity occurs when a function has a hole. So whenever you have a hole, that's a removable discontinuity. The limit exists but does not equal to the value of the function. And example 1. So it says given the function f of x and then we have a rational function there. So it's asking where is f of x discontinuous. Okay, so when is a fraction undefined? When the denominator is equal to 0, right? So here also take your denominator, set it equal to 0 and solve. You should be able to do that in your head too. At x equals -4, this function is going to be discontinuous. So the next one, it asks me, how can we tell the difference between a hole and a vertical asymptote? Okay, so this is a little tricky, not very difficult, but you need to understand. Anytime you're able to cancel the denominator, then you will have a hole in the graph. But if you're not able to cancel the denominator, there will be a vertical asymptote. Okay, so how do I determine whether it's a hole or a vertical asymptote? Take this function and try to simplify it. Usually simplifying means factoring it. So I'm going to do f of x is equal to numerator. How do I simplify the numerator? Factor it. I need two numbers that add to 11 and multiply to 28. So it'll be 7 and 4, right? Over x plus 4. What happens here? The denominator didn't simplify any further. So here I can cancel the x plus 4 and the x plus 4. So now what can I conclude? I was able to remove this discontinuity, right? Didn't we say that it is discontinuous at this? We're able to remove by canceling it. That's why it's called removable discontinuity. So at x equals -4, let's write this down. There is a hole. Therefore, what kind of discontinuity it is? It is removable discontinuity. I'm just going to abbreviate it. That's discontinuity. Okay, so again I'm going to say it. If you're able to cancel out the denominator with something in the numerator, which we did in this question, then there is a hole, and that means it's removable discontinuity. That's where the word removable comes from, that you were able to remove the discontinuity. Okay, and if you were not able to, then it would be a vertical asymptote, and we'll see more questions along the way. So it says for the next thing, do each of the following functions have a removable discontinuity? Why or why not? So you have to find out if they do have a removable discontinuity or not. So the first thing I told you is what? Simplify it. So let's simplify it. There's a GCF here, which is 2x, and you're left with x squared minus 4 over x. What happens to your x's? They cancel out, right? So what are you left with? 2 times x squared minus 4. That's your function, right? So since you were able to cancel out your denominator, then it is what? At x equals 0, there will be what? A whole, right? There will be a whole, and therefore this is what kind of discontinuity it is. I'm just going to write here, removable discontinuity. I'm abbreviating it. Okay, part B. Look at the numerator and the denominator. You can't really simplify it, right, over real numbers. So there is none. There is no removable discontinuity. There's no vertical asymptote. There's nothing. The next one, can I factor the numerator? So yes, I can. And it will be x squared. Give me two numbers that add to -4. So it will be x plus minus actually 3 and x minus 1, right? And in the denominator, the same AM method, it'll be two numbers that add to 2 and multiply to -15 are 5 and -3. Okay, so now what happens here? Look, this cancels. So in this question, we have a whole and a vertical asymptote. So there are two things. So let's write it out. Whole at x equals 3. So that's what? Your removable discontinuity. Removable. I can't spell. Removable discontinuity. You have to know the names of these. I'm just going to abbreviate that, right? And then you have a vertical asymptote at x equals -5, right? Because we were not able to cancel it. So if you can cancel, there's a whole. If you cannot cancel, there's a vertical asymptote.